Hello guys, we're just going to quickly kind of go through some of the stuff that we would have taken some more notes on in class. First we're going to talk about matter, which normally you would have read about in your book, but we're going to pretend here that we are in school and you just read it, and we're going to go through it a little bit differently than we normally would. So you guys learned about the states of matter when you were running through the younger grades here. So we're not going to spend a ton of time on this, but anything that has mass and takes up space is considered matter. Now, a lot of times if we were in our classroom, I would say to you, is air matter? And some of you guys might have to think about that, or all of us think about it for a minute, because we sometimes forget that air does have mass. So if we weighed a balloon with air in it and a balloon without air in it, we would note that there is a mass to it. So air also definitely takes up space, right? So that's a piece of it too. So volume, which we kind of mentioned in our lab that we did with density, is the amount of space that something takes up. So we take the length, width, and height of something if it's a solid, right? And then we say, for example, centimeters cubed or millimeters cubed or meters cubed, because it's length, width, and height. It's 3 measurements, right? But if it's a liquid volume, clearly we don't take the length, width, and height of something liquid like water, right? We use a graduated cylinder that would have a liquid volume in it. So we would do it that way. And we would measure it in milliliters or liters, right? So to do that, we actually take a graduated cylinder that looks something like this. And of course, I would show you this if we were in class together, but I can't show it to you because we're not in class together in person. But you can see this picture here, and you'll notice that this dips down a little bit in the middle. So if we want to be really accurate when we're measuring in science, we always measure the meniscus as being right here. So it's the lower point, because it raises up a little bit on the side. And if it is measured there versus right here, you're going to get a different measurement. So you need to be careful. So that's the meniscus, and that would be how we would take the milliliters or liters of a liquid volume. And then this is just a sample over here on the right of taking the length, width, and length, width, and height of a cube, and we would take 1 times 1 times 1, right? So it would be 1 meter cubed if it were a solid volume, right? So they're just showing you that there. So we said the mass is the amount of matter in an object, and weight is the gravitational force that is exerted on an object. Now, on Earth, we use mass and weight kind of interchangeably, but you have to be careful because weight is dependent on the gravitational force of an object, but it depends on where you are. So your weight on Earth might be different than your weight on the moon or your weight on, let's say, Mars. So if the planet or the body that you're on, because the moon is not a planet, weighs, if it's less massive, right? The moon is less massive than the Earth, then you're going to weigh less because the gravitational force is less. Yes, there's gravity on the moon, but it's just so much less than it is on Earth. Then your weight is going to vary. So your mass, it stays the same, right? The amount of matter in you, whether you're on the moon or the Earth, is the same, but your weight is dependent on the gravitational pull, which is dependent of the mass of the planet or the body you're on. So if you were on Saturn, for example, we all know Saturn is way bigger than the Earth, right? You would be like smashed into it. You would weigh so much. So this is a great chart that I want you to be familiar with. We're going to go over it a couple times this year. So mass is a measure of the amount of matter in an object. It's always constant no matter where the object is in the universe, and it's measured by using a balance. We use digital balances, electronic balances at QP. This is kind of an old school one in this picture. It's expressed in kilograms, grams, or milligrams. We talked about the metric system. Weight, it's the gravitational force on an object. So it varies depending on where you are on the Earth, right? And where you are in the universe. So the weight is measured by using a spring scale, kind of on the far right there. And we use newtons. Now you and I use pounds here in the United States, but newtons is technically correct. All right, so we talk about a brick versus a sponge, right? Both have the same volume. They look the same on the outside. Length, width, and height is the same, but a brick has more mass, so it's going to have more gravitational pull. So that's important to note. And then we have to bring up inertia, right? So that's the tendency of an object to resist any change in motion, speed, direction, unless a force acts on it. Think about your iPad right in front of you, right? It's going to resist moving unless something moves it. You pick it up. A giant wind comes flying through your house and knocks it off the table, or somebody else comes and takes it, right? So it doesn't want to move unless a force acts on it. Same thing happens with a baseball. When you throw a baseball, it's going to stay in motion unless a force acts on it. Somebody catches it. It hits something, or gravity pulls it down to earth, right? And there's also air resistance, right? So that's fighting against the movement. So that baseball should stay in motion forever and ever and ever unless a force acts on it. Air resistance, gravity, all sorts of stuff. So a larger mass is harder to stop. Imagine if I pitched a bowling ball at you right now, right? It would be a lot harder for you to swing your bat and change the motion of a bowling ball versus a smaller baseball. So a larger massed object like a brick is going to have a lot more inertia, right? Tendency to stay moving, or obviously stay put on your desk. It's going to be harder to move a bowling ball than it is to move a baseball off your desk. So that is kind of talking about the states of what matter is, and we'll be getting into the states of matter very, very soon. So that is an important piece to remember. The next thing that I want to talk about is going to have to do with physical properties, which we're going to be going over very, very soon. So a physical property is a characteristic of a substance. It does not involve a chemical change. So when we describe something as a certain color or a certain size, that is a physical characteristic, right? So you're going to be watching a video, or some of you may have already watched that, related to physical and chemical properties and changes. So when we talk about a chemical change, that's a little bit different. We'll be talking about that soon. So some examples of a physical property when we describe something: the shape, the strength, the odor, the flexibility. Does it conduct electricity? Is it a magnet? And its density, which we just talked about. Those are all physical properties, right? So they're things that we would look at, for example, if it conducts heat or electricity, right? Is it solid, liquid, or gas? Is the density the mass per unit of volume, right, of the substance? That might help us understand its physical properties. Malleability: can it be shaped like aluminum foil into another shape? Ductility: can it be drawn into thin wires? Is it soluble? Does it dissolve in another substance, like Kool-Aid dissolves in water? So we talked about density. We're not going to spend a ton of time on that, but a golf ball is denser than a table tennis ball, right? Because the golf ball has more compact mass in that space, right? So we already saw an example of this too, where you can take different liquids, right, in a graduated cylinder. So corn, oil, water, shampoo, dish detergent, antifreeze, and maple syrup, right? The maple syrup's on the bottom because that's the most dense. So these are examples of physical properties. So now we're going to talk about chemical properties real quick. And again, we're just going to go over this first, and then we're going to spend a little bit more time doing some stuff with it. So we're just getting kind of the background of this down. Just making sure you guys can see it. Okay, so chemical properties. This describes the substance's ability to participate in chemical reactions. So what are some examples of ways that we would describe something, some properties, right, of a chemical reaction? So if it's flammable, if it reacts with oxygen or doesn't, right? Or how does it react? So if any of you guys have ever seen a car that's rusty, right? This picture was in your science book, which you don't have yet, but this iron in this old car has a chemical property of reacting with oxygen. We call that rusting, right? So the bumper on the car still looks new because that's made of chromium, and it does not react with oxygen. So cars start to rust after a while because they are exposed to oxygen in the air after a lot of time. So think about a chemical property as it's a little harder to observe. So the physical property of this nail, right? We could bend the nail, that's changing its shape. And we could talk about the state of matter, right? Rubbing alcohol is a clear liquid at room temperature. That's a physical property, right? But if we were describing that nail, right, as reactivity with oxygen, right? It reacts with oxygen and it forms iron oxide, or that rust that we were just talking about. And then flammability is a term that we would use, right? So rubbing alcohol is able to burn easily. So chemical, we can easily, not easily observe it. Physical, we can observe it without changing the identity of it, right, when we describe it. So characteristic properties are things that we use to figure out or describe things, right? So it might be something physical, like density. It might be something chemical, like flammability. But some examples here of both, right? Chemical and physical characteristic properties would be density, solubility, flammability, reactivity. So here's the crux of what we're going to learn here. So chemical changes, one or more substances change into an entirely new substance that now has completely different properties than what we started with. Think about when you bake a cake, right? You throw all these ingredients together and now you have this wonderful cake when you're done. You can't separate those ingredients back out. You have something completely different when you're finished. So some other examples that your book used, soured milk. I love that picture, by the way. And then, it's not the same as what it started, right? It's regular old milk and then these bacteria change it. Chemical reaction. Effervescent tablets that you might take when you're ill, those are completely different when you end with what you start with. Hot gas formed from hydrogen and oxygen to make the shuttle blast off. The Statue of Liberty, right? She ends up needing to be restored every now and then because she's made of copper, but the elements in the air, right? The wear and tear of the weather, it starts to make her look green, right? Instead of that copper color because of the oxidation, right? With the moist air. And so the chemical changes over time make her green. So baking a cake is a great example. What you start with and what you end with are very, very different. Still all the same stuff there, but now it is very different. So it's hard to reverse it. Think about it that way when you're thinking about what's chemical and what's physical. So to tell the difference between physical and chemical, you need to ask yourself, did the composition change? Did what I start with end up being different as far as what it looks like, right? Can it be reversed? And usually 9 times out of 10, that means if it cannot be reversed, that it's a chemical change. So here's a great example, right? Grinding baking soda into a fine powdery substance, right? When it was a big chunk is not a chemical change. It's still, main components are there, you haven't changed it. But if you take baking soda and vinegar and add it together, you have a solid powder with a liquid vinegar, right? And now you get carbon dioxide gas. That's a chemical reaction. All that stuff is there, but it has completely changed form. So that is a chemical change, okay? So we're gonna come back together now that you've watched these videos and talk about some other stuff.